Good day, everyone. I hope that you are enjoying the course so far. This is the first demonstration video to help you using the commercial finite element software SAP2000. In our course, we'll intensively use this state-of-the-art finite element analysis and design software to model different types of engineering problems. In this video, we'll focus on modeling one-dimensional bar problems using SAP, and I will consider the example that we did in chapter 3. So for unidimensional problems, we always refer, or our reference is the x-axis, which is along the center line of the bar. And to refresh your memory, we did the formulation in chapter 3 for two-noded bar element, where at each node you have 1 degree of freedom, which is a displacement u. So you have u1 at node 1 and u2 at node 2, where L here is the length of the element, E is Young's modulus, and A is the cross-sectional area. So in this problem, we have to divide our bar into 3 elements, and the reason behind that you have a change in the cross-sectional area. So you have A1, A2, and A3, and also you have a change in loading. So a general rule, whenever you have a change in the geometry, change in material, or a change in loading, you have to divide. So here, the minimum number of elements that we need to use to model our problem is 3. Where element 1, so for the element number, I will put it inside a square, and for the node number, I will circle that to make a difference between the node number and element number. So element 1 is connecting node 1 and node 2, while element 2 is connecting node 2 and node 3, and element 3 is connecting node 3 and node 4. So as you can see here, regarding the boundary conditions means that which node you are preventing it from translation. So node 1, u1 is equal to 0, so we have here a boundary condition, and also at node 4, u4 is equal to 0. Which means that for this problem, as we discussed in class, that we have 2 active degrees of freedom, which is u2 and u3. So as you can see here, given in the example, we have the length of element 1 is equal to L3 is equal to 4 meter, and L2 is equal to 5. Also we have EA1 is equal to EA3, where E is Young's modulus, and we have the value for EA2. We need to calculate also the cross-sectional area, because we're going to need that in SAP. So with simple calculations, you're going to find that A1 is equal to A3 is equal to 0.002 meter square, while A2 is equal to 0.005 meter square. It is simply by dividing EA by Young's modulus, but just make sure that you are consistent in terms of units. Regarding the loading, so the bar is subjected to a distributed axial force, where P1 as force per unit length, it is 150 kilonewton per meter. P2 is 210 kilonewton per meter, which means that element 1 is subjected to a linear varying axial force. P2 is equal to P3 is equal to 210, which means that element 2 is subjected to a uniform axial force. And finally, P4 is equal to 150 kilonewton per meter, which is equal to P1. So you have here again linear variation of the load along element 3. So before we move to SAP and discuss how can we model this problem in SAP, I would like to provide a quick review and highlight on important concepts regarding what we did in solving this problem using hand calculation in class. So quickly, we started with the stiffness matrix to formulate the stiffness matrix, the global stiffness matrix. And we started first locally, element by element. So for element 1, this is element 1, we did formulate the stiffness matrix locally, where the first column is associated with u1, and the second column associated with u2, and the same for rows. Then element 2, which is connecting node 2 and node 3. So we have here again u2, u3, u2, u3, and finally element sorry, I have to change to be consistent. So element 1, element 2, and element 3. So again here U3 and U4. And simply what we did, we assembled the global stiffness matrix before applying boundary conditions, which is basically 4 by 4. So you have U1, U2, U3, U4, and same for rows. So how we did quickly, how we assembled this stiffness matrix, element 1 is connecting node 1 and node 2. So as you can see, I will highlight in red, this is the stiffness matrix for element 1. If I give a blue color for element 2, so element 2 is connecting node 2 and node 3. So you're gonna see that you're gonna find that the stiffness matrix for element 2, you have an overlap at the degree of freedom U2, U2. That's why we have a plus here, and that makes sense because element 1 and element 2, they have a common node, or they are connected through node number 2. If I give a green color for element 3 is connecting node 3 and node 4. Node 3 and node 4. So we have the stiffness matrix for element 3 overlapping again at U3, U3. So we have addition here. For any nodes which are decoupled means there is no connection between them, like U1 and U3, they are decoupled, so you always have zeros. So this is how we assemble the global stiffness matrix before applying the boundary conditions. Then we did similar steps for the load vector. So we did find the load vector for element 1. So this is element 1. So element 1. And load vector for element 2. And load vector for element 3. And finally, we did assemble the global load vector before applying boundary conditions. So the first row here is associated with the degree of freedom U1, second row is U2, then U3 and U4. So if you be careful that I give here the symbol hat, because so far we didn't apply the boundary conditions. So if you try to find the determinant of the stiffness matrix to solve for the unknown degrees of freedom, you will find that the determinant of this matrix is 0, which means that this is a singular matrix. So that's mathematically that this matrix is, you cannot find the inverse of this matrix. But what's the physical meaning of that? The physical meaning that your system is unstable and you have a rigid body mode, so you have to apply the boundary conditions. So you are missing your boundary conditions here. So our boundary condition that U1, based on this problem, that U1 is equal to U4 is equal to 0. This means that we have to go back here and to apply the boundary condition for U1 is equal to 0. So I'm going to cancel the first column and first row. To apply the boundary condition for U4, so I'm going to cancel column number 4 and row number 4, which means that at the end of the day, my stiffness matrix after applying the boundary conditions will be reduced from 4 by 4 to 2 by 2, which is this part. And again, it is a square symmetric matrix. We're going to do a similar approach for the load vector. So to apply the boundary conditions again, I'm going to cancel the first row because U1 is equal to 0, and I'm going to cancel row number 4 because U4 is equal to 0. So the load vector after applying the boundary conditions will be reduced to 2 times 1. Accordingly, you're going to have here the stiffness matrix but now it is after applying boundary conditions. And also we have here load vector after applying boundary conditions. And accordingly, we have delta. This is a typo. Delta, which is your unknown degrees of freedom, which is 2 times 1, is going to be U2 and U3, which is the active degrees of freedom that we need to solve for. So if we substitute by the values that we have for the length of the element, EA values, the values of the intensity of the load P, so we'll end up solving for the unknown displacements, and we did solve for U2 and U3, and we ended up with such values. So that's the first step, that you solve for displacements. Then you go back locally, element by element. Locally here you take the elements separately from the system. So for element 1, which is connecting node 1 and node 2, we know from the boundary conditions that U1 is equal to 0, and U2, that's coming from the finite element solution. So using the shape functions, we can calculate the displacement at any point within the element or between the nodes. So simply the expression for displacement as function of the local coordinate S. What's the local coordinate? The local coordinate that S at the midpoint of the element is equal to 0, S at node 1 is equal to -1, and S at node 2 is equal to 1. So using this local system, we can calculate the displacement at any point, knowing the S value of this point. So it is half, since U1 is equal to 0, so this term will cancel. So it is half times 1 plus S times U2, where U2 is given by this value, which is 0.00905 from our finite element solution. To find the strain, so the strain is basically du by dx, or we simplified that in a very simple form, that it is the change in length per unit length. So I can write it as U2 minus U1 over the length of the element. So basically it is 0.00905, which is U2, minus 0 over the length of the element, which is 4. So right away it will give you this value, which is dimensionless, because the strain here is the change in length per unit length. If you multiply the strain times Young's modulus, you'll end up with the stress. And as we expect, the stress along element 1, it is constant stress. And we explained in the lecture that the two-node bar element, because we are starting from linear displacement field or linear polynomial, so the first derivative, which is the strain and the stress, will be constant. If you do the same exercise considering element 2, you will find that the stress and the strain equal to 0, because simply the displacement at the start of the element or at node I and the displacement at node J, which is the end of the element, both are equal. So the element is experiencing a kind of rigid body motion, so you don't have any strain or stress. Considering element 3, you're going to end up that the strain is similar to element 1 but with negative sign, and the stress is also constant, negative 452. So far this is the solution coming from the finite element method using two-node bar element. And we need to understand now if this solution, or to make judgment if this solution is accurate or not, or exact or not. So I'm going to compare here the finite element solution, which is in dotted line, to the exact solution which comes from equilibrium or structure analysis. So as you can see, this is the bar, and that's the distributed load acting on the bar. So from the finite element solution we agreed, so let's refer to the finite element in red. So element 2, we have 0 stress. On element 1, our stress is constant, which is 452, and then here drops to 0 at element 2, and it's negative 452 on element 3. So this is element 3, element 2, element 1. Now how can we come up with the exact distribution, or the exact solution of the stress, or the exact distribution of the stress? So simply, if you go and calculate the area under this curve, So you can end up with the total force acting on the bar, which is the area under this curve. It is 2,490 kilonewton. If you divide this value by 2, this will give you the reactions at the supports right away. So for example, to calculate the stress at this section, which is the value, which is 622.5 megapascal, this number is coming from the reaction. So if you calculate stress, let's call this node 1. So stress at 1 is the reaction, which is 1,245 divided by the area of this section, which is A1. So this will give you right away the value of the stress here. So if you do this exercise at different sections, but be careful at node 2, you're going to see a drop in the stress because you have from the left of node 2, the cross-sectional area is A1, while from the right, you'll have different cross-section area, which is A2. So at this node, from left, your stress is going to be this value, which is 262.5 megapascal, while from right, because the area is greater, which is 0.005, so you'll have drop in stress. This value is wrong. The correct value is 105. If you continue doing that at node 3, so at node 3, the exact value of the stress from left is going to be negative 105, and from right is going to be negative 262.5. So this value is 262.5, and finally, and definitely all of that is compressive stresses, this value is 622.5. So based on our understanding, we need to understand what's happening here and why the finite element solution is not capturing the exact value. So basically, the best thing to understand, because the load acting on element 2, it's a uniform distributed axial force, so we're expecting that the exact solution will give us linear variation in stress. So this is linear stress. That's from exact. Let's write it in blue because we referred to exact as blue. So exact is blue. So this is linear stress. So for element 2, you start with tensile stress, which is 105, and then it drops linearly until it reaches negative 105. Now the finite element solution, because you are modeling this part from node 2 to node 3 using one element, the capability of this element that can give you only constant stress. So what's trying to do now, that it's trying to find the average of this value, which is the average of positive 105 and negative 105, so you end up with zero stress. So that's why you have this kind of error in stress. The same thing happens here. By the way, this figure is not accurate, and please correct that in the notes, because the load here, since the load is linear, so I'm expecting a quadratic variation in the stress, not linear. So this actually, it's not a line, it's a curve. Like this is quadratic. So this is second order, which is varying from 622.5 to 262.5. So again, the finite element solution is giving you 452, which is a kind of average between the values 622.5 and 262.5. So that's why here we have this kind of constant stress distribution from the finite element along element 1, and the same here in element 2. Now the question is, how can we capture the exact value of the stress or to reduce the error? As you can see, we need definitely more divisions, especially in the part where you have high variation in the stress. So you need to divide definitely element 1 into more divisions, and also the same thing for element 2 and element 3. In SAP, before we start SAP, there is no bar element in SAP. Actually, we have a 3D frame element, which we have to limit the number of degrees of freedom in the nodes to reduce it, or we can say that we reduce the element from being 3D frame element to a bar element, one-dimensional element. So that's why in SAP, when we're going to model this problem using 3 elements, you will find that SAP right away captures the exact solution. Like, you don't need high divisions because it's a higher order element and we are reducing the number of degrees of freedom. So the element, you can think about it like in our 2-node bar element, we started with linear interpolation, like A plus BS, because simply we have only 2 nodes or 2 degrees of freedom per element. So we understand why we start with linear. So now think about a 3D frame element where at each node you have 6 degrees of freedom. You have 3 translation plus 3 rotational degrees of freedom. So definitely this is the displacement field here. When you start assuming a displacement field, it's very high order polynomial. So that's why this is a high order element. So now let's move to SAP to see how we're going to model this example using SAP. And I will always refer to the geometry from this page here. So first let's do some cleaning to erase this part, because I want to discuss with you how you can develop the geometry of this problem. So simply in SAP, the definition that we're going to do one-dimensional analysis, that again our coordinate system, this will be X. In SAP we always model in XZ plane. So this will be always Z direction in SAP, but we will see how we ignore the Z direction and we consider all our degrees of freedom along X. So first of all, to define the geometry, we're going to define what we call grid lines. So you need to think about it as guidelines, a grid line passing through the nodes. So I would say that we need 4 grid lines. So grid line number 1 passing through node 1, 2 through node 2, and 3 and 4. So we need 4 grid lines. The challenge here that you don't have equal spacing. This grid line you have 5 meters, and this is 4 meters, and this is 4 meters. So we'll see how to overcome that. So before we move to SAP, I want you to understand how any finite element package works in general. So any FEM software. For any FEM software, actually we have 3 parts. Number 1, what we call preprocessor. And number 2, what we call the solver. By the way, the solver, it means this is the black box. Like you don't contribute in this. You just, when you click run, there will be some mathematical operations done in the black box. And then finally post-processor. So SAP is user-friendly, as you will see now. We start with the preprocessor, where we define the following. We define number 1, the geometry. And then you define the material properties. And also you define section properties. And definitely you need to define loading, or cases of loading. You define also boundary conditions. And later on, we can also define design codes if you need to do design. Okay? Within the solver here, from whatever information you provide, you can think about it. Same steps we did in hand calculation, the solver will do similar steps, that it assembles the global stiffness matrix before applying boundary condition, the global load vector based on the loading that you define, and it defines what are the degrees of freedom. Then it uses the boundary condition that you're going to apply to find the load vector after applying the boundary conditions, the stiffness matrix after applying the global stiffness matrix after applying the boundary conditions, and then starts first thing to solve for degrees of freedom or the displacements in case of bar. Once you have the deflection or the displacements, you can solve for stresses in bar or moment and straining actions and shear in beam problems. How to present the straining actions or how to find deformed shape. So this would be from the post processor. So here number 1, we check deformed shape and also like displacement values. In case of bar, I'm focusing on bar today. Also, you can show in graphs or tables straining actions or internal forces. This can be axial force or axial stress in the bar. It can be moment and shear in the beam and so on. So this is a general idea about any finite element commercial software package. So now let's move to SAP. So this is the interface for SAP 2000, and as you can see, it's a graphical user. It's a user-friendly graphical user interface. So if you go to File, similar to any software, you can start a new model or open for a model that you already have. So we're gonna start a new model. Sorry, we're gonna start a new model. We need to decide first about the units, so you can choose the units. So in our problem, the units will be kilonewton and meter. You have different options. You can start something ready from the template for advanced structures, or you can start from blank. So we're going to start from a grid only case. And as we agreed that our grid, we're going to have the number of grids along x-axis, we need 4 of them. We need only, since we are modeling a unidimensional problem, so I will need only one. I need only one grid along y, and also we need one grid in z, because you are solving everything in one dimension. So this is what we need. Now, what's the spacing that you need between the grids? We have different spacing. So for now, I will assume that the spacing in x direction, I will assume it as 4. That we have the length of all elements as 4, and I will show you how to change that. Now in y, you cannot provide 0. We don't need y, but you cannot provide 0, so I will keep it as 1. And the same thing for z. Okay. So now we are done. Here it's asking you first grid line location. Usually we keep the first line location of the grid at the origin, which is 0 for all x, y, and z. It's going to provide you right away with 2 view windows, as you can see, a 3D view, and always we work in XZ. So as you can see here, XZ, so I don't need the 3D, so I'm going to move to XZ view. So we have here 4 grid lines as we need, but this grid is not accurate, because if you look to the coordinate systems, the spacing is always 4 between the grid lines. So if I right click anywhere, I will go and choose edit grid line data, because I want to edit that. So the grid that we have, it's called global, so I'm going to modify. So it's telling you that the first grid line is at coordinate 0 and at the ordinate 0, which is x ordinate, and B4, and grid line C is at 8. It's easier to go with the spacing. So if you click on a spacing, it's telling you that the spacing between A and B is 4, which is correct. Now the spacing, the second one, I want to change that to 5. So I'm going to change that to 5. So now, if you look to the ordinates back, you'll find that the ordinates are updated. If we click OK and OK, as you can see, the grid is updated according to what we need. So this coordinate system, if you check here, it tells you what's x, y, and z for each node. So if I go here, that's 0, 0, x is 0, here x is 4, x is 9, which that's what we need, and finally x is 13. So the first step that you define the grid, which is the guidelines for your geometry. Now, if you go to define, the beauty of SAP, and also same thing for ETAPS, that even it goes with the sequence of the logic that we discussed, which is the preprocessor. That the first thing you need to define the material. So I'm going to define material. So by default, you have a kind of material which is concrete and steel, but we're going to add a new material. You can define material based on a specific design code, but we'll go with user material, like user's general one. So I'm going to define a steel material. What we need here, keep in mind that your stiffness in the bar is EA over L. So in this step, actually, when we define the material, I'm defining E. And we are not considering the on weight, so I don't worry about the weight per unit volume. So what I need, also there is no Poisson's ratio, that's a one-dimensional problem. So what I need to define is only the value of E. So E here, based on our example, it is 2 E5 megapascal. Okay. Let's switch to this to make it easier. So it's 2 E5 megapascal. It's easier to write megapascal, so SAP right away. Okay. Sorry guys. So it is 2 E5 megapascal. So it can adjust right away to the units that you have, the default units that you have, just to avoid any mistake with unit conversion. So now we defined E. I will call this material steel. And now we have our own material ready. Now we need to define the next step. We need to define like the section properties, because we have different area, right? So I'm going to define, don't forget, there is no bar element in SAP. So we're going to define frame sections. There is a difference between import and add. Import, we'll use that later when we need to import like built-up sections, which is already built-up sections from the steel design handbook, or ready cross-sectional area as concrete rectangular sections and so on. So I'm gonna add new property, and then we're gonna use other here, because I won't go with built-up sections. I'm gonna go with a general section. So as you can see here, for general section, I can define the area. So for this area, we have the first one, which is 0.002. So now I'm gonna call this section, I'm gonna call it bar A1. Okay, so to know that this is the cross-sectional area A1. So now this section, the material, we defined the material before. That's why the first step, you need to define the material. I have to link it to the material that we defined, which is called steel. So now we have E times A. That the black box will understand right away that will take E value from the steel multiplied by this cross-sectional area. To make sure that everything is correct, go to section properties. We have the area defined here. Definitely it's a one-dimensional problem, so we don't worry about moment of inertia, about shear area and this kind of things. Leave it as one, the default values. Section modifiers, we'll discuss that later. This is in case you would like to reduce the stiffness. To give you a quick kind of idea about this part, think about this bar. If it is a concrete bar and you're going to have cracking, so there will be reduction in the axial stiffness, so you can reduce the cross-sectional area based on what you are expecting in terms of reduction of the stiffness. But for now, we are not considering that. So again, we defined a general section where we defined only the area and the material is steel. So far we have EA is ready for A1. We can make a copy of this. So I'm going to add copy of the property, and I'm gonna call this one bar A2. Okay, so bar A2, it has the same material, steel. The only difference that the area now, instead of being 0.002, it is 0.005. So I'm going to change this to 5. Okay, so now we have both cross sections. I'm going to do one thing here. Since we have A1 is equal to A3, so I'm going to modify this and name it also A3. So this means that we can use this cross-sectional area for both A1 and A3. And you can give it any name according to what you think. It's reflecting, just not to be confused, it's reflecting the cross-sectional area that you have. So now we have the material properties ready, the cross-sectional area is ready, and we can start drawing our frame element. Don't forget, so far it's a frame element, but we're going to see how to reduce it to make it a bar element. So you can go to draw frame, cable tendon, our element is frame, or you can go and use the shortcut here, frame element. So as you can see, it's a straight frame element. It's telling you what's the cross section. Is it A1, A3, which are the same, or is it A2? So I'm going to start with element 1. If you click here on node 1, and then you take it up to node 2, and then click on the left button again. So this will give you element 1. Now you have to be careful. You have to change the cross-sectional area to 2, and then connect element 2 from node 2 to node 3, and then go back again, because this is element 3, which is cross-sectional area A3, and then connect from node 3 to node 4. And then we can close this. Either you click escape or you click on select to get out of drawing frame element. Before moving forward, I would like to discuss something very important, which is something called local axes. So if you go here, which is set display options, if I make the joints, instead of being invisible, I'm going to make them visible here. So as you can see, this is node 1, node 2, 3, and 4. We can also show the labels of the frame elements. So element 1 is connecting node 1. Like if I right click on this node, it's going to tell you that the label here is node 1. Okay. So element 1 is connecting node 1 and node 2, and element 2 connecting node 2 and node 3, and so on. There is something very important to understand, that there is something called local axes. So global, we are working in terms of XZ plane, but locally, if I show the local axes now for the frame means that for us it's the bar. So I'm going to switch to 3D to understand. So the local axis is following the right hand rule. Always the red one, we call it local 1. So that's one axis, number 1. And then the green one, it is 2. So if you go from 1 to 2 following the right hand rule, you will find that the 3 axis, which is the one which is out of plane, which is perpendicular to XZ plane. So this is the local axis for the element. There is another local axis for the joint. So the local axis for the joints, in such case, it is not different in terms of local 1, but as you can see, it has difference in 2. So the green is 2. So following the right hand rule, you have 1 in red, 2 is green, and 3 is going up. So you have to be careful that the local axis for joints might be different from the local axis of the frames. So that's something on the side to understand. So let's go back. So far, let's summarize what we did. We did define the material, we defined the cross-sectional area for each bar element, and we draw the elements 1, 2, and 3. Now, what is left for us to define the load? So I'm going to go define load patterns. By default, there is always the dead load is considered. So I'm not going to consider this case of loading. I will not run it, and I will show you how to do that later. So I'm going to define a new case of loading. Let's call it distributed axial. And this type of load will go with other. I'm not going to define a specific case of loading. Self-weight, if this is 0, this means for this specific case of load, don't consider the on weight. Don't consider the on weight. So it has to be 0 here because we are ignoring the on weight. So if I add new load pattern, so I have, sorry, it's called dust. So let's go again, correct this, distributed load. and I can modify. So distributed axial force type is other, self-weight multiplier is 0 because we are not considering the own weight of the bar. And now since I defined this case of loading, now I can start thinking about how to assign the load. So if we go and click on element number 1, we can go and assign frame load. It is a distributed load, and when you go here, you will find not only the case dead, which is by default, you will find a new case of loading, which is called distributed axial force that we defined before. And we need now to assign a distributed load, and you have two options, either to assign it globally or locally. So I'm going to discuss both. Number one, globally, you are applying a load in X direction. So one way to do it, that it's along X. And is it force or moment? It is force. It is not uniform. It is varying linearly. So we have to use this. But be careful. I'm going to explain that. This is relative distance versus the load. So I can define the load at node 1, which is at this relative distance 0 of the element, and at node 2, which is a relative distance 1 at the end of the element. So the best way to do it, get rid of 3 and 4, make them zeros for now, because I don't need those. I can define the load through only 2 nodes because it's varying linear. And what I can do at relative distance 0, which means at the start of the element, P1, it was 150 kilonewton per meter. And that's our unit so far, that's kilonewton per meter. While at node 2, which is at relative distance 1, the load is 210. So I can now apply. So as you can see, I applied this load, which is varying from 150 here to 210 here. Okay? Now I'm going to do the same thing for element 3. I will start with this element. I'm clicking on element 3, where element 3, the load is varying from 210 at the start to 105 at the end. But I'm going to do it differently. I'm going to do it using local. So for local, we know that 1, which was the red line, it is going through the center line of the element. So to apply the load locally, which is similar to X global, you have to choose 1. And be careful, at 0, it is 210. It's 210. And at 1, it is 150. 1 here, that's the relative distance. So again, relative distance 0, this means at the start of the element. Relative distance 1, it means at the end of the element. So if I'm going to apply it, we have to make sure that we are correct. That's right, it's 210 here and 150 here. Now, for element 2, you have a uniform load. So you can use this kind of trapezoidal load, or you can make your life easier. You can make your life easier that you define along local axis 1 simply uniform load right away, which is 210. And you click on the element and then apply. So now we are good. Okay, and then okay. So far we did apply the load, but we have a challenge now that the elements that we are using, it is a frame element, and so far your structure is unstable because we didn't apply any kind of boundary conditions. So I need your full attention here to understand how we're gonna reduce the degrees of freedom of this element from being 3D frame element to a unidimensional bar element where you are expecting only 1 degree of freedom per node. In SAP, if you go to analyze, set analysis options, by default SAP does 3-dimensional analysis. So as you can see, 3 translation and 3 rotation are active. So this is not the case. If I click that my analysis in XZ plane, so right away it's going to deactivate 3 degrees of freedom, and you're going to have translation in X, translation in Z, and rotation about Y. And that makes sense because we are doing XZ analysis. But still, this now is reduced to 2D frame element instead of 3D frame element. So still that's not what we are looking for. So what we are looking for, only to have translation in X. So I'm going to also deactivate the vertical displacement and the rotation about Y. So now as you can see, my degrees of freedom now are reduced, instead of 6 degrees of freedom, only 1. And then we'll click OK. The second part now, how to apply the boundary conditions. Our boundary conditions, again, don't forget the local axes for the joints. I'm going to highlight that again. In 3D, I want this node to prevent it from translation along 1, which is the red. Like, see, it's one-dimensional problem. So in order to restrain this node, you have to restrain the direction 1 locally, which is in direction of X globally. So let's go back. I'm going to choose this node, and also, which is node 1 and node 4, and I'm going to go and assign joint restraints. So now we need to restrain what? We need to restrain locally only translation in 1. Restrain here means that you are preventing it from translation. So I'm going to apply. So now you are good. Okay. So I'm going to remove the local axis just not to confuse you. So far we applied the boundary conditions. We did apply the load. What's left for us to decide about what cases we need to run? So set load cases to run. By default, the dead load is there. We agreed that we are not gonna run it, so I will click do not run case. And also by default, there is modal analysis to give you the mode shapes. So I'm gonna also cancel running this case, and the only case to run is the distributed axial force. Okay. Definitely we didn't save the file, so if I click OK, this will ask me to save the file. So before doing that, I will save the file. So let's lecture 3. Let's give it a name. Example 3. And then we can go, either you can run from here or go again back to set load cases. You can show in the background what the run, what's the log file is running, and I'm going to talk about the log file, and you can say run now. So the program, as you can see, that's the solver now is working. It's assembling the global stiffness matrix and so on. So now, first thing, always I prefer that you check the details of the run. So it's going to show you the log file. This we call it log file. And as you can see here, it's not giving you any kind of warnings. And let's understand what's happening here. It is telling you that this problem, you have 4 joints and you have 2 restraints. And you have 3 elements, which is three frame elements, but to reduce them to bar. And you have 1 cases of loading. And as you can see, even we relate that to the lecture, that the total number of equilibrium equations is 2, because you are solving 2 equations in 2 unknowns. And then the analysis is complete. So the first thing that you need to show is the deformed shape. So if you click again, if you click here, this will give you undeformed. So this can give you the undeformed shape. And this will give you deformed shape. So if you click on the deformed shape, we have only 1 case of loading. If you have more, you can change which case that you want to show the deformed shape. So we have 1 case of loading. So it will give you the deformed shape. If you start the animation here, it will give you how the bar is deforming under this load. If you hover on one of the joints and then right click, it will give you the displacement. Definitely it's 6 degrees of freedom. That's the general. But for us, because we are limiting the element to simulate a bar problem, so we have only translation in X. If you recall from the lecture, we did also have the displacement at node 2, which is 0.00905, and our units is in meter here. The same happened here at node 3, which is the same value, 0.095, which is matching our displacement. So as you can see from the finite element solution, we have the same displacement, which is matching the exact. However, what we got from the finite element method, that the stress on element 2 it was 0, on element 1 it was positive 452, and element 3 is negative 452. So let's go here and check. First thing, you can check on the reactions, which is the joints here. For this case of loading, if you click apply or OK, it will show you that the reaction at each support is 1245 kilonewton, which is matching what we concluded from the exact solution. Now let's check the stresses along this bar. You can check axial force, or it can be stress, and don't forget it has to be stress along 1, which is the local one. So if you do that, I will show the stress distribution. And this is, as you can see, again, SAP is going to give you the exact solution. So if we click on element 1, let's change the units to make it easier. Let's make it in megapascal, which is Newton millimeter. So if I just hover on element 1 and then right click, you will notice that at 0, at distance 0, or at the left of the element at 0 millimeter, your stress is 622.5, which is the same that we concluded from the exact solution in our example. If you move to the end of the element, you're going to have 262.5 at distance 4 meter or 4000 millimeter. And that's exactly what we concluded. And it is positive, it is tensile. You can also, by the way, show values. Like in this plot, you can show values and you can take screenshots. You can show values here and you can take screenshots to provide that, or you can show it in tables as well. So for element 2, the stress is varying from positive 105 megapascal to negative 105 megapascal, which is matching also what we did in our example. So as you can see here, one of the things that we should notice also, that this element, the stress is varying linearly. And that's our expectation because the load is uniform along element 2. While in element 1 or element 3, your stress, actually SAP, I hope that you can see that, SAP is providing you with quadratic variation. It's not linear, it is quadratic. Like if I will try to zoom here to show you this element. This is not a line. That's not linear. That's a second order curve. So that's, as you can see, that's the beauty here of modeling this bar using SAP. So this ends our first video. I hope that it helps you to model one-dimensional problems. And in our second video, I will provide you with how can you model translational spring in case of bar problems. Thank you so much.